ball. Larson, explain why N1 and N2 should be pushing into the ball.
Because the weight is pushing towards.
Forget about the weight. When you describe normals, I know you've been trained to describe it in terms of weight. Forget about weight. Just talk about it in terms of the normal, because the normal is created by the surfaces, right? So why do these two normals go up this way?
It's touching.
It was touching this bar, and the bar is pushing up on it. So the bar is pushing up on it, normal goes this way. Bar is pushing up on it, normal goes that way. It's what it's experiencing, which is a compression force. Okay, let's do the next one.
Do we write that N1 and N2 equal the same and then N and E equal?
Say that again?
Would we write that the normal and normal 1 and normal 2 are equal in magnitude?
In the end, they are equal, and why are they?
Because it's supporting that one ball.
Say it again.
It's supporting the ball with
And what else? Not just because it's supporting the ball.
same direction.
It's totally, the bars are totally symmetric, right? They're in the same direction. If the bars were like this and they were in different directions, then they would be supporting it differently. But this is totally symmetric. The weight of the cylinder has to be uniformly distributed, unless it wasn't, right? Aaron and then Lucas.
So do the normals from the ball cancel the normals from the bars on that third free body diagram like the tensions do?
I don't know, we would find out, maybe they turn out to be the same values. I mean, in the end, these right here, if we're looking at that free body diagram, if we did some of the forces in the X and the Y, and what Eric just said is correct, that NA and NB are the equal, and N1 and N2 are equal, we're gonna be able to solve that right there, because it's reduces to two unknowns. But I don't want to worry about the statics part, the equilibrium part. We're going to have a lot of practice on that. What I want you to have practice on today is drawing these free body diagrams. Because as you can imagine, if you draw the free body diagrams wrong, the rest of the problem is wrong, right? So you need to make sure that we know how to draw free body diagrams. Lucas?
So does that mean like at point C there's no reactions at that support?
There are reactions, but they're internal. Right, they're internal. Like both Lonnie and I are feeling each other right now, right? But they're equal and opposite, and they're canceling each other out. And you can't do statics to analyze it unless you separate us to calculate the value.
So if you're going to solve for like how strong the pin needs to be,
You would not draw that left free body diagram, because that left free body diagram is only going to allow you to find all those four normals. Everybody get that? If your goal is to find out what CX and CY are, that left free body diagram is not going to help. That left free body diagram is only going to enable you to find the normals. But in order to find CX and CY, maybe we would do that free body diagram on the left, because I can solve all the normals, and once I find the normals, then I can come back and pick one of the other free body diagrams. And we'll spend a lot of time on that. What's the most efficient way of solving the problem? Which free body diagram should we use? Okay, but right now I want us to get comfortable on drawing a free body diagram. Okay, let's do another one. Let's do 19. I want you to draw the free body diagram of AB and B, C, E. You have two free body diagrams you have to draw. Oh, okay. Well, let's draw it anyway. Good point. Sorry. They want you to draw a DF. So let's draw free body diagrams of all four of those bars. Is it hot in here? I'm feeling like it's hot. Can we open the window, the door? Or you guys get cold and close it. you guys finish already? Yeah.
Slightly more technical. Say your line.
Okay, you ready? Okay, we're up to Rachel. So Rachel, let's do AB first. So what needs to be drawn on AB? Okay, so what kind of support is this? They're both pins. So what did you draw? AX positive? So you drew AX positive and AY positive. And then BX you drew positive, and what did you draw BY? Negative? Negative? Okay. So Sarah, what about BCE now?
B and C are going to both experience forces in the y and x, so I do dy dx.
Okay, and how would you draw, based on what Rachel just drew, how would you draw BX and BY?
I would draw bx to the left,
Right?
and then I would draw by up.
Right. Because everybody has that, right? You have to draw an equal and opposite. And then how do you want to draw C?
Oh, then we can draw C up.
Okay, up,
Positive y.
positive Y, and
And to the right.
CX.
As far as E, I was debating whether or not I think it might be the collar on a smooth shaft.
Okay, so let's look at the pictures.
It's like it can move, but it could also just move.
So it's the one where there's like a pin inside a slot. So let's figure out what that title is.
So pin and smooth guide.
Pin and smooth guide. Okay? So a pin and a smooth guide, what could it resist, Sarah? This is a question you asked in
Yes.
class the other day.
Yeah, so, well, that goes back to, so it can resist in the X and the Y, but,
No, it can't. So in this case, this is a good one to do. Let's zoom in a little bit more. So it's a 2D problem,
Oh,
right?
it's just in the X, yeah.
So this is 2D. So it has the possibility, sorry. It has the possibilities of resisting a force in the X, a force in the Y, and a moment in the Z, right? That's the possibility. So let's think about this. Here, this guy could move this way, right? The two pieces could move relative to each other. It could go up and down,
Yeah,
but it can't move this way.
yeah, so you're
Right?
gonna draw
So you're
diagonal.
gonna wind up drawing E going in this direction. What is this? It's 1 to 1. So even though we think in terms of X going to the left and Y going up, in this particular case, we know it can move this way, and we know it can't move that way, so we're gonna draw what it could resist in this direction.
And how do you know it was 1 to 1?
Say it again, how did I know what?
How do you know E was 1 to 1?
Oh, because of this. See the bar from D to F, they have a little 1 to 1 here. And then as far as a rotation in the Z, think about this bar. If we look up here, we have this bar connected to this bar via this pin. If it wasn't connected anywhere else, wouldn't this bar be able to just spin on this bar because there's a pin there? It would be able to spin around, so it doesn't resist a moment. So the only thing it resists is a force perpendicular to that slot. Okay? Okay, so we're up to Janae. Let's do DF now.
So you would have to draw P.
Right? To the right. What else?
And then, would you draw E in the equal and opposite direction?
Yep. So E is experiencing the same thing as the other E is, right? They're both point E. The only thing is I have to draw it equal and opposite. So since I drew E up to the right, now I have to draw E down to the left.
And then you would have
What do I have at F?
force into the Y and X.
Right, Y. What kind of connection is there?
It's a pin.
Yeah. Jose?
So, would it be okay if you drew E, well, same, opposite directions, but pointing the opposite way?
Yeah, so at E, everybody look up here. Here, I could have drawn E up to the right or down to the left because I don't know which way it is. And if I drew it down to the left here, I would have had to draw it up to the right here.
And that's what I did.
Okay, that's fine.
Okay, cool.
Eric,
D is a pin, right? So-
say it
and
again.
D is a
D,
pin.
as in David, is, it looks like a pin, but since it's not connecting,
You don't
that's a
do
really
reaction.
good question. Everybody look at D. Is there a connection at D? There is not, because it's not connecting to anything. There's a hole there, and if they put another bar, then we probably would use a pin. But even though it has a circle, it's not connecting anything. That's all that's happening at that end, at D end of the bar, is that it's being pulled P. All right, we have time for one more. So I want you to circle these other three, and if you are the one who does not have the paper, then take a photo of it. 21, 25, and 24. Let's do 25. So it was 21, 24, and 25. 21, 24, 25. 21, 24, 25. Okay, so let's look at 25. It says the bent bar. So they wanted us to draw a free body diagram of the bent bar. Here's C, here's B, and here's A. Okay, so before we do even connections, where are we? Chris? What do we put in? Ignoring the connections right now at A, B, and C, what do I need to make sure I draw in here?
Ignoring A and B and C,
Yeah, what other forces are here that I need to draw?
the normals.
What normals? I don't see any normals. I see some
Well,
P's.
there's normal at A.
Well, I said to ignore A, B, and C. What other forces do we need to draw?
P3, P2.
Yeah, great. So draw the easy ones first. P2, P3, P1. Okay, now Chelsea, what is going on today? Let's read the words. The support at A is a journal bearing, and the support at B and C are ball bearings. So, what is a journal bearing resist? So go back in the packet pictures or the textbook pictures. What does it resist?
Two forces.
Two forces. And tell me, now that we have the X, Y, and Z axes on here, which forces does it resist? Let's do A first.
E and the Y.
Right. So an AY and an AZ. And then does it resist any moments?
Yes.
About which axes?
It would be about the C and the Y.
Correct. And I'm going to draw these guys positive. This is where you really should draw these pictures bigger, because look at how tiny I drew mine, and it's hard to see what's going on, and this is where you make mistakes if the drawings aren't clear. So I would have made a huge picture. I would have made a picture as big as this. So I have enough space to see what's going on. Okay, how about at B now? Nick, it's a ball bearing. So tell me what it resists.
So you're gonna get resisting the forces in the Y and the X.
By and Bx and
X. Then you're gonna resist a moment in the X and the Y.
check the ball bearing drawing. Because the ball bearing allows us to do some rotation.
That's right, you do get rotation.
I think you get rotations about X and Y too.
Yeah.
So I think a ball bearing is just Bx and By. Is that correct?
Yes.
Okay. And now let's do C. Nicholas. C is a ball bearing too. So what do we have to draw it in? What do we draw? What are the reactions at C?
X.
What?
X.
What X? Force or moment?
Moment in the X. The force in the X.
Force in the X, the X, and
The Z.
a Z. You can see how this picture is way too small. My free body diagram is way too tiny to be able to look at this later on a test when I'm stressed, to pick the right directions of the moments and forces. You gotta draw it bigger. So, I want you for Thursday, today's Tuesday, right? For Thursday, I want you to draw 21 and 24. Okay? And you guys, look up here, just to remember, so you need to watch the distributed load video by this Thursday as well, and we're gonna work on the distributed load homework on Thursday. So that means this Thursday, I want you to have 21 free body diagrams for 21 and the free body diagram for 24 done. Then I want you to, you have to watch the video for distributed loads by Thursday, and we'll work on the distributed load homework on Thursday. And then you have 2 things due on the 26th, which is when? Is that a week from today?
Yes.
No, it's the week of Thursday.
A week from Thursday? Okay. Okay, no more workshops